La relatividad general explica cómo el espacio y el tiempo emergen para constituir la columna vertebral de la naturaleza. Pedro Ferreira. Transcurrido casi un siglo desde que Albert Einstein dio a conocer al mundo su teoría de la relatividad general, distintos grupos de investigación ponen a prueba su validez a escala del universo. Pedro Ferreira es uno de los científicos que trabaja en esta línea desde Oxford. En este capítulo de Redes, Ferreira hablará con Punset de algunos fenómenos astronómicos que derivan de las ideas de Einstein y repasará las piezas que aún faltan para completar el rompecabezas de la relatividad. Y en su sección, el Sapunset planteará otro aspecto que también despierta muchas incógnitas, pero cuyo papel es crucial en ciertos aspectos de la vida cotidiana: el inconsciente.
Hace un siglo, más o menos, el astrofísico de Cambridge, Arthur Eddington, espetó al resto de la comunidad científica que solo un par de personas en el mundo comprendían la teoría de la relatividad general de Einstein. Curiosamente, el mismo Eddington difundió en 1919 dicha teoría al mundo anglosajón y quizás gracias a él hoy mucha más gente de la calle que aquellos dos está familiarizada en cierto modo con la teoría de Einstein. Y muchos científicos, no solo los dos que afirmaba Eddington, la comprenden a la perfección. Uno de esos es el astrofísico Pedro Ferreira, que lleva años explicando con éxito la teoría a sus alumnos de la Universidad de Oxford y que hoy en Redes nos ayudará a entenderla un poco mejor.
Pedro, it is true that even today I don't quite figure out, and I have tried many times to understand this theory. It would be marvelous to take advantage of this opportunity to talk with you, to understand a little bit. And so maybe it would be good to start with comparing the idea that people had of the universe, the one I had when I was a child, that this was something smooth, and without great interruptions. And then what you came later on to tell us that it wasn't smooth at all, the universe, that the structure of the universe was something very abrupt and touching one thing with the others. And so, do we know now what on earth is the structure of our universe?
Well, that's I think big transformation in our understanding of the universe has been over the last 30, 40 years, and you're absolutely right. For many years, I think one of the great things to come out of Einstein's theory of general relativity is this prediction and confirmation that the universe is this smoothly expanding space-time, ever-expanding space-time, incredibly smooth, the technical term is homogeneous. But if we look up at the sky, we see galaxies, and we see clusters of galaxies, and we see lots of light and then very little light, and it's very complex and structured. In the early 1960s, even before, but really in the early 1960s, people began to say there has to be a connection between the two, this smooth picture and this very complex structured picture. And I think one of the great things of the last 30, 40 years has been to be able to explain the structure. So I do think now we understand what we call the large-scale structure of the universe, the complexity of the universe, this clashing that you talk about, much, much better and incredibly precisely in a way that we didn't before.
When you throw a planet in the sky, something happens with the space-time.
Yes.
It becomes smaller or whatever. And there was no way to explain what was happening unless you try to to understand what Einstein was saying.
In some sense, yes. I think we have to be fair to Newton. So Newton's law of gravity was, and is, remarkably successful at explaining a lot. And so, for example, it explains almost everything about the solar system. You can explain the way that galaxies move and rotate, and very much using Newton's law of gravity. But if you want to get the big picture, if you want to see where everything comes from and where everything links together, you can't ignore that we live in this immense universe and that everything is connected. And Newton's theory of gravity was not able to explain the evolution of the universe, how it would link to, as you say, the galaxies and how things behave. The interesting thing about Einstein's theory of gravity is one of the interesting things is this conceptual shift in which space and time stop being this place where you put things and have a life of their own. So as you say, if you put a planet in space and time respond and deform and adjust. And vice versa. The way that planets move through space and time feel the way that space-time is adjusting. It's a very elegant, slightly bizarre way of thinking of the world or the universe, but that's what Einstein gave us.
And mysterious also.
Yes.
Cuando tiramos una piedra en un estanque, provocamos olas en el agua. La teoría de la relatividad puso de manifiesto que algo similar sucede en el universo. Según Einstein, la fuerza de la gravedad no es una fuerza en sí misma, sino la consecuencia de la deformación del tejido espacio-tiempo por la presencia de un objeto celeste con mucha masa, como una estrella o un agujero negro. El movimiento o choque de estos objetos origina ondas en este espacio-tiempo. Estas son las llamadas ondas gravitacionales. A pesar de tener evidencias de que estas ondas existen, los científicos aún no han conseguido detectar ninguna. Igual que las olas de agua en el estanque, las ondas gravitacionales pierden fuerza cuando se alejan del lugar de origen. Al llegar a la Tierra, son extremadamente débiles. Y para observarlas necesitamos experimentos extremadamente precisos.
You have here, for instance, in your book, in the state of the universe, it says, this is a theory with its warped grids of space-time wrapping around deep, desolate throats of nothingness. Is this the universe?
Well, it's a colourful way of saying this thing, which is that space-time gets a life of its own. It deforms, it warps, it changes, it curves, and one of the fascinating predictions is that if you put a lot of stuff in one place in space-time, it'll warp it so much that it'll create what are known as black holes.
That's it.
And these black holes basically suck everything into it. So, I like to think of them as these throats of nothingness where stuff goes in and doesn't come out. So I think it is. I think that it's one of the great and fascinating things which, in some sense, made it quite difficult for people to accept this theory in certain limits.
And how do you know about the existence of a black hole? I mean, nobody ever has seen any black hole. That's what you say on one side,
yeah.
But on the other side you say, but you can feel it.
The way that you see it is by its effect on other things. And we've seen, I think the most fascinating evidence for a black hole is at the center of our very own galaxy. If we look at the center of our very own galaxy and we map the way that stars move around the center of the galaxy, they move in incredibly tight orbits. They're very curved, incredible, and the only way that stars can move on such a tight orbit is if there is this immense gravitational pull coming from a very small place. in space-time. And the only explanation for that is really a black hole.
And what on earth happens if two black holes clash with each
That
other?
has been a challenge, an open problem for decades. People have an idea that if two black holes collide, they merge and form one black hole.
Uh-huh.
But it's richer than that. It's quite interesting because the black holes typically they will fall into each other, spiral in, and then suck each other into into one big black hole. And then they'll emit this burst of what's known as gravity waves, ripples in space-time, incredibly energetic, that then propagates out. So it's like this explosion of space-time.
When you look at the universe like that, you say maybe you see nothing but gravitational waves like in a pool.
Yes.
No? There will be some. What on earth do you mean by these gravitational waves?
What I mean by gravitational waves is I think I've given this picture of space-time as this thing which is alive. Right? It's not just this thing that sits there. It's thing that folds when you put a mass in. And I imagine that you knock it, space-time will ripple.
That's it.
And gravitational waves are these ripples in space-time. Now, the universe should be full of gravitational waves because there's all this energetic stuff going on. They're just incredibly hard to see. And so one of the, I think, great challenges, experimental challenges, is to measure these gravitational waves. It would be a fantastic confirmation of Einstein's theory of general relativity.
0,00000000000000001 metro. Este sería el desplazamiento que notaría nuestro cuerpo si por él pasara una onda gravitacional. Un movimiento 1.000.000 de veces más pequeño que el tamaño de un átomo. Dado que las ondas que nos llegan son tan débiles, los científicos han tenido que utilizar la imaginación para poder medir esas pequeñas variaciones en el espacio-tiempo. Una forma de detectarlas sería con un dispositivo llamado interferómetro. Supongamos que tenemos dos barcos exactamente iguales en medio del mar. Los preparamos para que, a la misma velocidad, recorran la misma distancia en direcciones perpendiculares y regresen al punto de partida. En una situación de calma chicha, sin olas, estos barcos llegarán exactamente en el mismo instante. Sin embargo, si a lo largo de su camino pasa una ola, esta modificará el trayecto de los barcos, siendo ligeramente distinta la distancia que recorre cada uno. Como consecuencia, no llegarán juntos al punto de salida. El interferómetro para detectar ondas gravitacionales parte de una idea similar, pero en lugar de barcos, utiliza haces de luz láser, que nos permiten ser mucho más precisos. Con su uso podemos detectar diferencias de tiempo mucho más pequeñas. Medir una de estas ondas gravitacionales es una de las piezas que nos falta para completar la teoría de la relatividad general. Conseguirlo supondría superar uno de los grandes retos de la cosmología moderna.
Do you think we are getting out of our old ideas of the universe? In other words, do you think when people talk now about new theories like string theories and other things, when they talk about new fashions to understand the universe, are they really pointing towards the future or they are pointing towards nothing?
I think one of the great things is the power of thought in modern physics, and it's these visionary ideas, often quite wacky ideas, quite strange ideas that take us forward. As you were describing when Eddington made his comment about Einstein's theory, I mean, Einstein's theory was, when he did it, was just completely off the wall. I mean, he had to learn a new form of mathematics, had to educate himself to phrase his new theory in a way that no one really understood at the time. I think now people understand it. People are afraid of it. I think there is a folklore now where people are scared. If they don't know it, they're scared of learning the mathematics. But I teach it at Oxford, and I think my students love general relativity. It's just a great thing to learn. But it was a wacky idea. You mentioned string theory. String theory is, I think, very difficult to understand if you don't know string theory. But I think it's a great thing because I think very clever people work on it, and interesting, even if it's not the right theory, interesting things will come out of it. So I'm a believer that it is forward looking, but we need to think of these different things and pursue them all and see where we go.
Llevamos unos 100 años poniendo a prueba la relatividad general de Einstein, sus hipótesis, sus predicciones y otros fenómenos que de ellas se derivan. Por el momento parece que estas cuestiones se van cumpliendo, aunque como siempre cada respuesta que constatamos desata nuevas preguntas. Cada vez diseñamos experimentos más ambiciosos, más caros y más increíblemente sofisticados, como el colisionador de hadrones de Ginebra o el interferómetro que hemos conocido en este capítulo. Y pese a nuestros esfuerzos, las nuevas preguntas siguen surgiendo. Pero eso es bueno. Nos da alas para innovar, para progresar y generar nuevo conocimiento. No me digan que no es fantástico.